Je sais pas. Oui, vous m'entendez. Bon. So my turn to thank the organizers. So I will give a talk about two experiments we did in the last years. All the results are not that recent, but they have been obtained in the lab with my collaborator Valérie Vidal. Henri was a postdoc, and we work in collaboration with two labs in Chile. One in Santiago, and the other one is in Curauma. This is I don't know the French. C'est à l'avant-port in Valparaiso. Um, okay, so I will show that tiny perturbations, mechanical perturbations, can trigger large-scale events. Just a few words about the motivation. In the lab, we have an activity close to geophysics, and reading a little bit literature, we came to the conclusion that people report that big earthquakes can trigger aftershocks for sure, but other earthquakes. And these earthquakes are triggered by very, very small events. They can be in other places that are at long distances. And the question was mainly, if you look at the literature, they say that they report the strain, the local strain, so at the secondary event. The strain can be of the order of 10 to minus 6, 10 to minus 7, rather small, or the velocity, the associated velocity of a vibration that propagates is about a few tenths of centimeters for a load of a fault which is small. So the question was, how come such a small perturbation can trigger a large event somewhere else? If I connect the talk with what the subject here of a meeting, I was myself more interested in the plastic events in granular materials, and you have a plastic event locally in a granular material, and you want to know if it will trigger or not another event, and even you want to know if this is not by amplification the reason why you go from a static pile to of granular materials to a material that will flow. So this is the main motivation of the work, and I will explain two configurations. We have one in the lab. The first one is in the lab in Lyon, and the second one is in Santiago in Chile. So the first configuration is very simple. It's not new. It's just a friction experiment, a classical one. The idea is just to, in fact, pull a block, a solid block, across a substrate. And in solid friction, usually what you want to know is what are the properties of the dissipation produced here by the frictional contacts between the block and the substrate. The slider is pulled with the help of a spring, and if you record the elongation of a spring as a function of time, you can see that the force, classically what you observe is that you load the system, and then you reach a maximum force, it slides, and then you release the stress, and you observe this kind of stick slip, which is a very classical result. I just want to stress out that the threshold here is just the load that the system can sustain, and that the average is an image of a dissipation. Okay. So this is the classical stick slip. And here are the results obtained by Nasuno and Golub in it was at the end of the 90s in Haverford. So you can observe if you do this experiment with a granular bed, you can observe this stick slip regime, and changing the driving velocity, you can go through an inertial regime where you observe oscillations. In fact, just the spring mass system is oscillating, or even reach a continuous sliding. Okay, and these experiments were performed with a sliding block which is light, 10 grams, in order to avoid the wear of the grains. You are not breaking the grains, and you hope you are not changing the physical properties of the grains, even of the surface. So now my question will be the following. I don't change the experiment, but I add to this experiment a mechanical vibration. I want to know how it alters this picture. So we reproduced the experimental setup in the lab. So we have a slider. It is put thanks to a cantilever spring. It's not a linear spring. We just measure here the deflection of a spring, which gives us the position of a slider in the frame of a laboratory and also the force we apply to it. And we can change the driving velocity. And we have a granular bed. We can use, well, the system is rather large. We have the box is more than 40 centimeters long, so we can pull this slider, which is about 8 centimeters in size, in length, across a long distance. And the typical grain diameter will be between 45 and 600 microns. The slider mass is from 30 grams to 200. If you go above this, the slider is sinking in the grains. We can change the stiffness of a cantilever spring, the driving velocity, and we add to this system vibrations. So I will spend some time explaining what kind of vibration we are imposing. In fact, we have a shaker which is held on the side of a table, just like this. And we just vibrate it at a frequency of 10, 80, 100 hertz. It's not a large frequency, a high frequency. In fact, we are moving the table as a whole. It's not a wave propagating in the grains. We are just changing locally the gravity, maybe, I can say. And also, the main axis of the vibration is perpendicular to the system. We didn't want to kick the slider up and down, because we don't want it to jump. No, we don't want to change, in fact, the shear stress, meaning the stress in this direction. So we are pulling in one direction, but we impose the vibrations perpendicular to this axis. And so okay, so this is the system. So what do we observe? These are our results. So F star is just the force we apply divided by mg, the mass times g. In fact, it's a kind of image of a frictional coefficient. So without vibration, A omega, A is the amplitude of a vibration, omega is the frequency, angular frequency. So without vibration, we have a nice stick slip. Okay? We can measure the maximum force and the average. We impose vibration, and here I give a velocity associated to the vibration, A omega. What we observe is that the average is decreasing. Is that in average the system is dissipating less. Okay, and we also observe that the threshold is decreasing. The system sustains less and less the load, and we observe also that for a given velocity, the stick slip disappears. We have a transition. We don't change the driving velocity. We just impose vibrations that are perpendicular to the velocity, and we observe a disappearance of a stick slip. This is done increasing the amplitude of a vibration. So what we will report is the average, F star bar, and the amplitude of a stick slip. And this will be done in the next picture, but we observe qualitatively first that we have a decrease of the dynamic friction coefficient, the dissipation, the average of a signal, a decrease of the amplitude of a stick slip, okay, so a decrease of a threshold, and that the continuous sliding is reached for a small value of gamma, because if we, instead of reporting the velocity associated to the vibration, we report it in terms of the reduced acceleration, the acceleration associated to the vibration divided by the acceleration due to gravity, we are at a value of 0.03 at the transition. it has nothing to do with G. We are not just shaking enough to fluidize the system. So here I report the amplitude of a stick slip as a function of the acceleration associated to the vibration, as a function of a driving velocity. So we check that we are changing the shear rate, the main shear rate we impose, and we observe that the transition of gamma, the acceleration at the transition, does not depend on the shear rate. Okay? Now, what I do is that I display the amplitude of a stick slip, changing the frequency of a vibration. So, and I report the result as a function of the acceleration associated to the vibration, and we see that we have a huge dependence of the result on the frequency. Okay, but it means that the acceleration associated to the vibration is not the appropriate control parameter. But if we display the same results, so as a function of the velocity associated to the vibration, we observe a collapse of the data, whatever the driving velocity and the frequency of associated to the vibration. So this is the dissipation. The blue line says that when we introduce a velocity of a frame of reference, we have a decrease of a dissipation, and we have a decrease, okay, of a stress the system can sustain. And the point is that the dependents are not the same. One is more or less linear for the dissipation, and the other one is parabolic. So at one point, they cross, and at this point, the system goes from stick slip regime to a continuous sliding. Okay. And what is interesting is to have a look at the value of the velocity here. The value of velocity here is about 100 microns per second, and does not depend on anything here, meaning the shear rate, nor the frequency of a vibration. And we did test changing the driving velocity, the frequency of a vibration, the spring stiffness, the grain size, the relative humidity for the grains that are of a size larger than 200 micron. They don't stick, and we can introduce humidity without having a cohesive material. We changed the shape of the material and the shape of the grains and the material the grains are made of. We didn't change much, but we changed from glass to ceramic particles. We changed the depth of a granular bed and the slider surface area, and the result is that this velocity does not depend on anything. Okay, at least not these parameters. So now I will talk about triggering the events. So I have a nice stick slip. Okay, so I'm pulling the system, and what I can do is that I can stop before the next sliding event. So at this point, the system is at rest but loaded. And now I want to know what is the effect of a kick. I impose a pulse, a mechanical pulse, and I just want to know what is the effect in this case. So the system is loaded. I have a tap. We have a relaxation of a stress. And we will report here just the sliding distance, or the drop of a force, as a function of the intensity of a pulse. And what you get is that if we load the system at 85 to 100% of a threshold, and I impose a kick, and I report here, the red dots, the traveling distance as a function of a velocity associated to the kick. So I have an accelerometer in the grains. I give a tap. I measure the acceleration, and I can, from this information, get the velocity associated to this kick. And what we observe is that we have logarithmic dependence, a log dependence of the traveling distance on this velocity. And it depends, and the slope depends on the initial load. If the system is not loaded, it will not slide. If it is close to instability, we slide over a large distance. Okay. And again, to collapse the data here is meaning to have the same here point, okay, because we have a log. It works well if we introduce a typical velocity a omega of 100 micron per second, so we recover the same results we obtained in the with harmonic vibrations. Okay. So these were the results for the first experiment. So the second experiment, the people in granular material do this kind of experiment with rotating drum. We have a rotating drum. It's about 20 centimeters in diameter. It's on a table. We have here a shaker. It's a magnetic shaker fixed to the table, and we just move a small mass here perpendicular along the axis of a drum. And we will just look at the avalanches. So here the grains are glass beads of about 1 millimeter in diameter. So if we report without vibration the angle of a free surface as a function of time, we observe a kind of stick slips, a succession of avalanches. And increasing the amplitude of the vibrations, we observe a decrease of the maximum angle the system can sustain, and up to, in fact, the continuous avalanching if the vibration is intense enough. Okay. So here, during the stick slip, we have what we call phi star, which is phi star, which is the angle of avalanche. Okay, the maximum angle, and we have, in fact, phi stop, the angle at which the avalanche stops. Okay, and this will be the amplitude of our avalanche. And we can report, in fact, this max and this mean, so this maximum angle and this minimal angle, as a function of the velocity associated to the vibration square divided by g times d, d being the diameter of the grains. Okay, and we see that we have a collapse of the data obtained at two different frequencies. Again, this is the velocity associated to the vibration, which is the control parameter and not the acceleration. And also what we can conclude is that looking at the value of v squared divided by gd, we can clearly see that if we have a length scale, it's not d, it's not the diameter of the grains that matters. Okay. But okay, the velocity is shown, is proved to be the control parameter again. And finally, we can trigger an avalanche. So what we do is we have to look at the inset here, is that we rotate the system until an avalanche is reached. We rotate it again to produce a given slope, and from that initial state, we give a kick to the system, and we observe the following avalanche. And what you observe is that if you load the system to this point, meaning to an angle which is below the angle of avalanche, you give a kick, and you display the point at the velocity associated to a kick, then the point, the system falls down on the curve you obtained previously in the continuous avalanche, or the continuous succession of avalanches. Okay. So these are the observations, and I come to my conclusions and also maybe an open point at the end. So from this experiment, what we observe is that the velocity and not the acceleration is the parameter that controls the system. Okay. That tiny mechanical perturbations can produce large events. Okay. This is, or if we impose an harmonic vibration, a continuous vibration, we can even make the system flow continuously. Okay. And this observation is important for the field. Okay, we didn't rescale the results, but we can see that it's not, maybe not that surprising that a small velocity associated to the vibration of a floor of after an earthquake can produce, in fact, the sliding of a fault. And but the open question is, what is the physical origin we can invoke maybe here? Okay, so velocity is the relevant parameter. And we can say maybe that the vibration plays the role of a temperature, okay, decreasing, in fact, the dissipation, so, and also the load the system can sustain. And if I want to go into details, but I have no answer, what we can compare, we can compare the energy of a vibration, we can compare it, for example, to the potential energy we need to overcome an asperity, meaning looking at the roughness of the grains, of the surface of the grains. If we do a numerical application for that, we end up with a size, okay, from the 100 microns per second we have, we end up with a size of 10 to minus 9, which is probably too small. So I don't think this is the right scale. And another possibility is to consider something proposed by Mathieu Villard, is that we can consider the energy you have to unlock two grains that are in Earth contact. So then the properties of a material will come from the Young modulus of a material, because under pressure the system can have intimate contact and the spheres deform a little bit. Okay, and this has to be tested, but we don't know how to do exactly this test to be really quantitative. We changed, I don't show the results, but we can change a little bit this velocity, but we don't control well what we are doing, so I don't want to show it. Okay, so this is the end.
Thank you very much. So now it's open for questions.
Yes, we did. So we change it, but it's difficult to change it without changing anything else. Okay, so what we try to do is that, for example, the last attempt was to use Piranha. Okay, so we cleaned the surface and we did that. But you alter the surface also. So if we have grains that are stiff, and if you alter a little bit the surface, you are also altering the Earth's contact. We don't know exactly what we are doing, so we have an image. Okay, so if I want to answer, so what we want to do, but we didn't do yet, is to use large grains like these ones that are 1 millimeter, and to have nanoparticles around. Okay, and change the nature of the nanoparticles that are around. Okay, because usually when you change the roughness, what you do is that you use this fluoric acid, or you are changing things in details.
Just why do you use this granular substrate and not a solid rough substrate?
So that we did also. In fact, we have the same results. We studied paper-on-paper friction. Okay, and we have almost the results, but the point is that so the typical velocity is the same. Okay, so which is a surprise. But if I go back to this picture, problem with solid friction is that instead of this curve, so we have a decrease of a dissipation, like we observe here in grains. But this upper curve is inverted. It's something like that. So it's more difficult to determine a threshold. Here it's very clear because you have a parabola in this direction. Okay, so the transition is not as sharp.
The maximum is decreasing, but not accelerating.
Yes, it's decreasing and they reach, but it's a tangential. So it's not as clear. Yeah. No, no. So what we did is that we used two different paper, cardboard or drawing paper, and you can change the velocity if the fibers, or it means also the roughness is larger. Velocity has to be larger, but the result is not as clear.
I wonder when you look at your periodicity, you have certainly Fourier transformed that stuff. I mean, when does the periodicity go bust? I mean, when do you go from one nice peak to something which is much flatter?
Okay, this we are working on that exactly because we have a problem in this. I can show you some. Here, problem is that this picture is a bit. Problem here is that you are talking about one peak we would have just for this system. But for a transform of a triangle is not a peak.
No, sure.
So this is the first point. But there is another point, is that the system, in fact, if you look in detail to this, okay, we used as a maximum load the system can sustain. We said, I said I take the maximum of the force, but I'm wrong. Nobody criticized that, but the system is creeping because here I don't have a straight line. And I have to determine exactly when the system is starting moving or creeping, at least doing something like that. And so we are working on that subject exactly, but on the filtering of it with people.
Use an autocorrelation function instead of Fourier transform. I mean, there are lots of ways how to get
Mm.
periodicity, but I think it's a stunning effect between your second and third picture there, where the periodicity goes away.
Periodicity goes away, but yes, it's probably not exactly periodic here. And yes, what we are doing exactly is that we are working on people that are specialists of this kind of questions, and we are really working about the way to filter this kind of signal and find and even get the statistics. And if, for example, to know if a large event is followed by a small one, and so we have this. We just submitted a paper last week on the subject.
If you apply continuous vibration in the system and this A omega x approach is a critical one, so do you see something on the surface of the granular materials? Do you see some excitation with the vibration or rearrangement with the granular particle and so on?
No, we didn't see any, but the acceleration, you have to figure out that the acceleration is 1,000 of g in the main experiments. It's very, very small because depending on how you choose your frequency, because if you change the frequency, you can change g. This picture holds as long as the frequency is low enough. Okay, at large frequency, you just fluidize the system.
So when you look at this, yeah, I mean, it looks like these sharp, these sharp edges are rounded off by the, as you would expect from some kind of thermal effect. So, what I thought when you were saying this is, it's probably the contacts between the bead and the surface, what exactly makes them sort of stick. But it seems, but then you said that as you increase the area of the sample, it doesn't matter. That would have increased enough. So, I mean, what gives rise to is it really the contacts between the beads and the slider that's resting on there, or is it that in front of the slider there is maybe a little bit of something that is blocking off, that is being removed, and this thing is, I mean, where is this effect coming from? From what is in front of the slider, or is it coming from what's below the slider?
I would say that if you consider the results we obtained with the avalanches, are just rejecting this. But the test, the real experimental test with the slider is that the slider is not squared. Okay, it's in fact it's a rectangle. We can change it, and the aspect ratio is such that we can make it slide in one direction or perpendicular one, and we observe exactly the same results. So it's really the surface area that matters, and not the pile that is in front. So this we checked. Also, what I didn't say is that we can control also the dilatancy. We have one sensor that permits to measure the motion in the plane, but we have also the out of plane information. We know if the slider is just moving up or sinking.
I think we have time for one last question.
So I'm just confused about how the piece of the story about the velocity of the sled, because at the beginning you showed us that the stick slip goes away when you pull fast enough, but then for the shaking you said it's pretty much independent of the velocity of the sled, right? So it must come back.
Okay, yes. There was a kind of, in fact, when in stick slip or in this pattern, you have between the stiffness of a spring and the velocity of driving velocity. In fact, you have a large range of velocity in which you can play, having the really nice stick slip. It is as long as this phase, loading phase. It's much longer than this decreasing phase. The slope here, the drop, the characteristic time is given by the spring mass system. Okay, and you can see here that you can change the velocity in a large range before one is reached the other.
But
Yes, in one, we were pulling faster, but on a range of multiplying the velocity by 100, maybe. Okay, it was coming from 10 microns per second to 1 millimeter per second.